Hello, my name is Kevin Shabahang. I'm going to present some explorations of associative nets that I carried out with the help of Professor Simon Dennis and Dr. Hyung-Wook Yim. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. Associative nets, or attractor nets, have been proposed as neurally plausible memory models capable of stimulus identification, categorization, bistable perception, among other tasks. An associative net is characterized by a state vector, a weight matrix, and a time update function. The state vector captures the momentary rate of firing across a set of hypothetical neurons. The weight matrix represents the synaptic strengths connecting each neuron with each other neuron. Encoding follows Hepp's postulate: what fires together wires together, where synapses between neurons that are active within a time interval are assumed to strengthen. It is implemented by taking the outer product of each trace vector with itself and summing the result into a weight matrix. The encoded information roughly corresponds to the correlations between the rate of firing of the various neurons. Here note that the weight matrix is both symmetric and square, and can be decomposed into a set of orthogonal axes or eigenvectors, each corresponding to a different eigenvalue. The eigenvalue captures the magnitude of variance captured by each given axis, or eigenvector. When the trace vectors are orthogonal to one another, they become the eigenvectors of the weight matrix. Here x is the state vector and is subscripted by time, or t, such that x sub 0 corresponds to the initial state. W is the weight matrix, and the m vectors correspond to the encoded traces. The Greek letter lambda corresponds to an eigenvalue, and the letter e, with the dot above it, corresponds to an eigenvector. We can rewrite W as the sum of the outer products of the eigenvectors, each scaled by the corresponding eigenvalue. Retrieval is driven by a time update function. The state vector is first initialized to a probe. Then the state vector is multiplied with the weight matrix to give the state at the next time point. This iterative process is continued until the change in state between two adjacent time steps drops below some small criterion. The final pattern is called a steady or equilibrium state. It is taken as the retrieved pattern. The process forces the original input to interact with the correlations encoded in the weight matrix. In the simplest case, we have a linear update function. The next state is simply the unit normalized vector matrix multiplication of the current state vector and weight matrix. In the limit, the linear associative net always settles to a single vector, which corresponds to the dimension capturing maximum variance in the encoded traces, or the dominant eigenvector. Expanding the update function makes it clear that the state moves towards the dimension with the largest eigenvalue in the limit. Anderson, Ritz, and Jones introduced saturation in the brain state in a box to remedy the dominant eigenvector problem. They constrain different states to lie within a box by imposing an upper and lower bound on the state vector activations. The system halts once it reaches one of the corners of its bounding box before it gets dominated by the lead eigenvector. Although the BSB enables a greater number of steady states than the linear associative net, the BSB is still limited. Critically, its set of responses is restricted to previously encoded traces. Hence, although it's a viable mechanism for pattern completion, it cannot readily generalize. The same is true of the Hopfield network. Because of their limited generalizability potential, associative nets fell out of favor in the wider AI community with the advent of multi-layer backpropagation networks. We present dynamic eigennets as a novel class of associative networks with greater promise for generalization. Dynamic eigennets incorporate short-term plasticity by temporarily summing the outer product of an input into the weight matrix prior to retrieval. Summing in the outer product enables the combination of the various dimensions of variance, or eigenvectors. whereas the weights combining those eigenvectors, that is their eigenvalues, remain static in the linear associative net and the BSB. Those weights are rendered dynamic with STP. Specifically, the weights along each dimension of variance are scaled in proportion to their similarity with the initial probe, which we have denoted here by x sub 0. We start off with some toy demonstrations meant to showcase some of the essential properties of the three types of associative nets we've introduced. In our toy demos, input to the system is a bigram encoded by concatenating two localist word representations together in sequence. In a localist representation, each word is assigned a unique vector, which has all its elements set to 0 except for one element at an index unique to each word. We encode two bigrams for the toy simulations, they cat and a dog, with the first bigram encoded slightly stronger than the second. Using the same weight matrix, we applied the three different update functions and characterized how the system settles when probed with one of 8 different patterns. We add some Gaussian noise each time we probe the system and repeat the process 1,000 times for each probe, tallying the probability of different steady states in the long term. The first two probes, they cat and a dog, correspond to previously studied items, and since we're adding Gaussian noise to the probes, they concern the error correction capacities of associative nets. The second two patterns correspond to the and in the first slot, respectively, with the second slots left empty. The underscores here denote empty slots. These two probes concern the pattern completion properties of the system. The second two patterns following, the dog and a cat, correspond to novel patterns that structurally align with previously encoded patterns. Finally, the last two patterns correspond to novel probes that contradict the structure of the encoded patterns. If the system is capable of generalization, it should be able to accommodate the novel structurally aligned patterns. However, it should reject novel patterns that structurally misalign with the stored traces. The following table shows the probability with which the linear associative net settles to different states. Different terminal states are shown separately across the columns for each of the different probes shown along the rows. For example, when probed with they cat, the system settled to the cat with a probability of 1. Indeed, with the linear associative net, the system always settles to the same pattern, the dominant eigenvector. This table shows the probability of different equilibrium states for the BSB. Notice that the BSB is capable of settling to the weaker bigram as well, a dog. As mentioned earlier, however, the BSB settles to a previously stored pattern even when probed with the 4 novel input patterns, that is, the last 4 rows. Hence, although the system is capable of both error correction and pattern completion, it cannot readily generalize. Finally, we show the probability of responses in a dynamic eigennet. As with the BSB, the system is capable of both error correction, the first 2 rows, and pattern completion, the 3rd and 4th rows. In addition, the system can settle to novel patterns that structurally align with previously encoded input, that is, the dog and a cat, but not if they violate the encoded structure. The system never settles to dog the or cat a. A look at the activation of different words after a probe shows the system settling dynamics. The vertical axis shows the momentary activation of the 4 words in the first and second slots, respectively. When we probe with the dog, as shown in the top panel, the dynamic eigennet reaches a steady state favoring the novel pattern. The word the, blue triangles, is most active in the first slot, and the word dog, black circles, in the second. Now in the bottom panel, when we probe the system with dog the, which contains the same words but in reverse order, the system pushes initial activations down to favor a structurally consistent steady state. Mont et al. Had subjects see a set of bigrams and judge whether each was grammatical. Each grammatical bigram included a possessive pronoun followed by a noun, her cat, or a personal pronoun followed by a verb, you think. Violations were introduced by either swapping the possessive pronoun with the personal pronoun, as in she cat, or taking the personal pronoun and swapping it with a possessive pronoun, as in your think. Mont et al. Found subjects were faster when responding to the grammatical bigrams relative to the ungrammatical bigrams. Similarly, in a lexical decision task, Collet and Segui found subjects to be faster to verify a second prime in two adjacent word-present trials, when the two words formed a syntactic bigram relative to when they did not. Importantly, the effect was much stronger if the first word was closed class, which roughly corresponds to function words, relative to when it was open class, which roughly corresponds to content words. The results were used to speculate as to whether open and closed class words are represented distinctly. We constructed a bigram-based dynamic eigennet and trained it on a large text corpus. We then sampled a set of bigrams from the text corpus, introduced the syntactic violation to the bigram, and probed the system with either the valid or invalid bigram. We used the vector length of the final state vector prior to normalizing as a measure of familiarity. We subtracted the familiarity for the invalid bigram from the valid bigram to get a measure of the difference in familiarity between the two. We did this for 9 different bigram types with 150 samples of each. We take the difference scores for each bigram type, take its mean and divide by standard deviation to get a measure of discriminability. The larger the value, the greater the familiarity for the valid bigram relative to the invalid bigram. Each row of the following table shows results corresponding to one of the 9 bigram types. Valid bigrams are shown in blue, and invalid bigrams are shown in red. The second column shows some examples, with the third showing the discriminability when memory for the bigrams is intact. In a fourth column, we show the discriminability computed for the bigram violations where we lesion memory for each bigram prior to probing the system. When discriminability is high in these cases, the system is exploiting general structural information as opposed to relying on memory for the bigrams. The black diamonds denote the bigrams corresponding to Mont et al.'s experiment, explaining the faster judgments for the grammatical bigrams in terms of greater familiarity relative to the ungrammatical bigrams. The open circles denote bigrams roughly corresponding to Collet et al.'s lexical decision results. Greater discriminability for grammatical bigrams provides a familiarity explanation for the faster lexical decisions. If you note the discriminability for the closed class relative to the open class bigrams, notice that discriminability remains high when we lesion memory for the closed class bigrams, but almost fully diminishes when we do the same for the open class ones. Hence, we can explain the greater syntactic congruity effect for the closed class bigrams as a result of the amount of structural information available. Given that all but one of the discriminability values are positive, the system can generalize based purely on structural content. In conclusion, augmenting linear associative nets with short-term plasticity appears to make them more conducive to generalization. Associative nets fell out of favor with the rise of layered backpropagation networks. However, backprop nets are far slower than people. They are incapable of one-shot learning. Hebbian systems remain a more neurally plausible alternative. I end this talk with the conjecture that perhaps human generalization results from recurrence in an STP-augmented associative network as opposed to slow error-driven learning. Thank you very much for your time. I would like to thank Professor Simon J. Dennis and Dr. Hyungwoo Kim at the University of Melbourne for their help on the current project. Be sure to check out their talks as well.